What's up? I'm Vin, and today I'm teaching the Extreme Value Theorem. So take a second to read through the theorem. Now, the idea behind this theorem is that if we have a function f of x and f of x is continuous, well, for one, if f of x is continuous, that means when we draw it, we have to draw it without lifting our pen off the page. But let's say first time around, I'm looking at f of x from a to b, and it looks something like this. So the function goes up, comes back down, and then comes back up again. So in this case here, notice that if we're looking for the absolute extrema, the absolute maximum is going to occur at this location over here, and the absolute minimum is going to occur at this location over here. So this is our absolute max, and then over here, this is our absolute minimum. And notice in this situation here that the absolute max and min are occurring at critical points where the slope is equal to 0. Now, another thing that could happen is we could have f of x look something like this. So now we have a new function f of x, and in this case here, our function f of x, let's say it looks something like this. So similar to before, except now if I call this point A and point B, notice now that the absolute maximum is occurring at A and the absolute minimum is occurring at B. And notice that in the middle here, between A and B, we have two critical points where the slope is equal to 0. So I'm drawing out this second graph here because when you're looking for absolute extrema, a very common mistake is that when students look for the absolute extrema, they only check the critical points. But you have to be very, very careful here. You also have to make sure that you're verifying the endpoints, because the endpoints in a situation like this could also be the locations of your absolute extrema. Now, one last thing to mention here, we could have another situation where, let's say we're looking at f of x, and f of x this time around, maybe one of the extrema comes at a critical point and the other one comes at an endpoint. So maybe we have something that looks like this. So we have a function, let's say we start here, it goes up, it comes back down, and then it looks something like this. So notice in this case here that our absolute maximum is occurring at a critical point. And notice that this absolute maximum, the critical point is a sharp turn where the function is not differentiable. So that's the sneaky type of critical point. But the absolute minimum is occurring over here. So this is our absolute minimum, and it's occurring at one of the endpoints. And then notice that we have, let's say, a critical point over here, and we have a critical point over here, but this is just a local minimum and a local maximum. So once again, we could have situations where the absolute extrema occur at a critical point or an endpoint. So now let's see how to apply the theorem. And for the first question here, we're going to find the absolute extrema of f of x, and we're on the interval from 0 to 5. And the first thing we have to do is find the critical points of the function. So we have to take the derivative of f of x. And notice that we have a product going on here. So we're going to use the product rule. And the product rule says when we have uv and we take the derivative, we're going to have u prime v plus uv prime. So we could define u to be x, and we could define v to be e to the negative x over 2. And just know that you could think of this as e to the negative half times x. This will be helpful when we have to take the derivative in a moment. So u prime is equal to 1, and then v prime, when we apply the chain rule here, we're going to have the derivative of the exponent is negative 1/2, and then we multiply by the original function here is just e to the negative x over 2. Okay, we could write this as e to the negative half x or e to the negative x over 2, but I'll write it this way because that's how it was in the beginning. So now f prime of x, we apply the product rule now. We're going to have u prime v, so we have 1 times e to the negative x over 2, so that's e to the negative x over 2, and then we have plus x times negative half e to the negative x over 2, so we have x times negative half e to the negative x over 2. But now to simplify this, what we could do is we could factor out e to the negative x over 2. So we'll have f prime of x is equal to, and now we have e to the negative x over 2, and we'll be left with 1, and then we'll have a negative here. We'll have minus 1/2 times x left, so we'll have minus 1/2 x. And now our goal is to find the critical points. So what we're going to do at this step is set f prime equal to 0. So setting this equal to 0 here, f prime of x is equal to 0 when the second factor is equal to 0. One thing to be mindful of is that e to any power is always positive. So since this is always positive, that first factor, we're only going to set the second factor equal to 0. And this one, if you just do the algebra quickly here, you'll see that x is equal to 2. At this part, you don't have to show a lot of work. It's just assumed at this level of calculus that you could do this algebra in your head. But if we had to do the work out, we would add 1/2 x to both sides and then multiply both sides by 2. But if we substitute 2 back in, you could see 1/2 times 2 is 1, and 1 minus 1 is 0. So this is our critical point. So now for the second step, we're going to plug the endpoints and the critical point into the function f of x. So we're plugging in x equals 0, x equals 5, and we're also plugging in x equals 2 This is our critical point. So let's go over to the y equals and we'll type in f of x. We have x and then we have e as second natural log and we're going to the power negative x over 2. And for this question here, we're interested in what's going on at 0, 2, and 5. So I'm going to press second window and I'm going to change the independent variable from auto to ask. That way we could just type in the values that we need. So we have 0, 2, and also 5. And notice just looking at the table here, we could see that at x equals 2, we have our absolute max, and at x equals 0, we have our absolute minimum, because this is the smallest y value and this is the biggest y value in the table here. But one thing we could do is we could also go to the window and we could change the minimum x from negative 10 to 0, and we could switch the x maximum over to 5. And now if we press graph, it's a little bit hard to see what's going on. We have a lot of extra space above and below. So I'll go back to the window and I'll make the y minimum negative 3 and I'll make the y maximum positive 3. That way when we press graph again, you could see that at x equals 2, we definitely have an absolute maximum here. And at x equals 0, we definitely have an absolute minimum. So now for the last step, all we have to do is identify the absolute maximum and absolute minimum value. So notice at x equals 2, we have our absolute maximum, and at x equals 0, we have our absolute minimum. Question 2, we're finding the absolute extrema of h of x on the interval negative 4, 3. So for this question here, we're going to start by finding the critical points of h of x. So we're going to do the derivative of natural log of this function. And just know when you take the derivative of something like natural log of f of x, the equation for this, you're going to have f prime of x over f of x. So this is the chain rule variant for derivative of natural log of a function. So we could apply that here. We're going to have 1 over the inside, which is x squared plus 6x plus 10, and then the derivative of the inside is going on top. So we're going to have 2x plus 6 on top. So once again, this chain rule variant is just helpful for questions like this. So now we want to know the critical points. So we're going to set h prime of x equal to 0, and this is true when the numerator is 0 and the denominator is non-zero. So we're setting 2x plus 6 equal to 0, and if we do the algebra here, we're going to get 2x equals negative 6, and then x equals negative 3. So this is our solution to this simple equation here. And now one thing to be mindful of is how do you know that the denominator is not 0 at negative 3? And the trick to this is thinking about the discriminant. So the discriminant tells you the type of roots you have with the quadratic equation. So if I look at the b squared minus 4ac term, that would give us 6 squared minus 4 times 1 times 10. And this is equal to, we would have 36 minus 40 is negative 4. And that's less than 0. So that tells me that our roots to this quadratic are imaginary, which means this quadratic never hits the x-axis. So it's never going to be equal to 0. So our domain is going to be good for this. So I know that this quadratic is always positive because let's say I were to plug in something like 0, I would have natural log of just 10 here. So I know the inside, once again, is always going to be positive. So I don't have to worry about the denominator being 0 here. So now this is our only critical point. So to close this out, what we're going to do is we're going to plug the critical point and the endpoints into the function h of x. So we have x and h of x, and our endpoints are negative 4 and 3. And then we have a critical point here at negative 3. So now let's type in, we're going to have natural log of, and we have x squared plus 6x, and then plus 10. And notice this time around, our interval, we're going from negative 4 to 3. So first I'll press zoom 6 just to put the graph back to normal. And I'm going to switch the window here going from negative 4 to 3. And let's see what this looks like. So what we have so far is it looks like our absolute minimum is occurring here at negative 3, and our absolute maximum is occurring at x equals positive 3. But to be sure, we could go to the table here and press second graph, and now we're typing in the endpoints are negative 4 and 3, but we also have a critical point at negative 3. So that means we're going to type in, we're going to have negative 4, we're going to have negative 3, and we're going to have positive 3. And notice that the picture does support what the table is saying here, that our absolute minimum is occurring at negative 3 and our absolute maximum is occurring at x equals positive 3. So now let's just transfer all these values over here. And once again, if we just look at this table here, we could see that the absolute minimum is occurring at x equals negative 3 and the absolute maximum is occurring at x equals 3. Question 3, we're going to find the absolute extrema of g of x, and we're on the interval from 1 to 7.5. So g of x, there's a product here, so we're going to use the product rule. So we'll say u, the first term in our product, is x squared, and v, the second term in our product, is 7 minus x to the 2/3 power. So now we're going to find the derivative of u. So u prime, we're going to use the power rule, is going to be 2x. And then for v prime, we have to use the chain rule. So we're going to do the derivative of the outside. We're going to keep the inside the same, and then multiply by the derivative of the inside. So we have 2/3 times 7 minus x to the negative 1/3. So there's the power rule to start, but we have to remember to multiply this by the derivative of the inside, which is negative 1. So v prime, if we simplify, is negative 2/3 times, and we have 7 minus x to the negative 1/3. So now we could say g prime of x is equal to, and first I'll do u prime times v. So we'll have 2x times this term here. So we're going to have 2x times 7 minus x to the 2/3 power. And then we have x squared times a negative. So we're going to have plus a negative or just minus 2/3. And then we have x squared, and we have 7 minus x to the negative 1/3. So for this one here, we want to find the critical point. So we have to know, when is g prime equal to 0? But also the sneaky critical point is, when is g prime undefined? Considering the function g of x, if we look here, the domain of g of x is all real numbers. So any location in g prime where g prime is undefined will count as a critical point of g of x. So to find out when g prime is equal to 0, I recommend turning this into a single fraction. So I'm just going to expand this a little bit. We're going to say that g prime of x is equal to, and we have 2x times, we have 7 minus x to the 2/3 power. And for the second term over here, after the minus, we're going to have minus, and I'm going to write this as 2x squared. And then in the denominator here, we're going to have 3, and then we're going to send this down as 7 minus x to the 1/3 power. So in order to make this work, what I'm going to do is I'm going to move this stuff over. Is we want to make common denominators so we could combine these terms into a single fraction. So this one over here, what I'm going to do is I'm going to multiply this one by 3 times 7 minus x to the 1/3 on top and bottom. So we're going to multiply by 3 and then 7 minus x to the 1/3. And we're doing this on top and bottom. And be mindful here, I could just say that this is over 1 right now. So we're going to say 3 and then once again 7 minus x to the 1/3 power. And now in the next line, what we're going to have g prime of x is equal to, and we have 2x times 3 is 6x. And then we have 7 minus x to the 2/3 times 7 minus x to the 1/3. So what I'm thinking here is the law of exponents. When you multiply something like a to the b times a to the c, this is a to the b plus c. So I'm seeing here we're doing 2/3 plus 1/3, which is 3/3, and 3 over 3 is equal to 1. So we could say that this is 6x, and I could say 7 minus x to the first like this, but an exponent of 1 doesn't do anything for this term on the inside here. So I could just say that this is going to be, once again, just 7 minus x. I don't have to write the power 1 on the outside like this. And now after, what we're going to have is we have minus, and we're just going to write our whole fraction here. Our denominator is 3 times 7 minus x to the 1/3, but after the minus we have 2x squared, and then we're over, we have 3 times 7 minus x to the 1/3. So we're getting a little bit closer here. Now we could combine this into a single fraction, and this is once again on bottom 3 times 7 minus x to the 1/3 power, and on top we're going to have 6x times 7 is 42x. And then after this, we have 6x times minus x is minus 6x squared. And then we have a minus 2x squared. So now we could simplify g prime of x. We could say g prime of x is equal to 42x. And now we combine like terms on top. We'll get minus 8x squared. And we're over 3 times. We have 7 minus x to the 1/3 power. So from this step here, now we could find the critical points. And the first kind of critical point we'll look for is, when is g prime of x equal to 0? G prime of x is equal to 0 when the numerator is equal to 0. And looking at this numerator, the first thing I want to do is factor this. So I'm going to take out a 2x here, the greatest common factor, and we'll be left with 21 minus 4x. So we could set this equal to 0. And the first factor, 2x, is equal to 0 when x is equal to 0. And if we set the second factor equal to 0, 21 minus 4x, this is equal to 0 when x is equal to 21 over 4. And this simplifies to 5.25. But if we stop finding critical points at this step, This is a very dangerous bear trap, and this is the most common mistake with questions like this, is that students only find the critical points where the derivative is 0. They forget to look for where's the derivative undefined, and we could say that g prime of x is undefined when the denominator is equal to 0. Okay, so we could say g prime is undefined when the bottom 3 times 7 minus x to the 1/3 is equal to 0, and this is going to give us another critical point here of x equals 7. But one thing to be mindful of is we're only looking at the critical points on the interval from 1 to 7.5. So we're not going to take x equals 0. We're going to take x equals 5.25, and we're also going to take x equals 7. So now for the next stage of this question, we're going to plug the critical points and the endpoints back into the function g of x. So the endpoints here, we're going from 1 to 7.5, and the critical points that we just found between these numbers are we have x equals 5.25, and we have x equals 7. So let's go ahead and type in g of x. We have x squared, and we're multiplying by, we have 7 minus x. So we have 7 minus x, and we're raising this part here to the 2/3 power. So this is going up to the 2/3 power. And now for this part, what I'm going to do is I'm going to press zoom 6 to put the graph back to normal. And notice this is what our function looks like. And we're missing some y values here. We can't see the rest of the graph. So what I like to do in situations like this is I'm going to press second window, and I'm going to switch the graph back to auto for a moment, the table here. So when we press second graph, we could see what some of these values are. And notice that between 1 and 7.5, that we're in the neighborhood here of, let's say, going up to y equals 40. But let me just play it safe here and go up to something like, let's say, y equals 60 and see what this does. So I'm going to change the y maximum to 60. And now I press graph, and notice now we could see a lot more of what's happening. But what I'll also do is I'll change the window to go from x equals 1 to x equals 7.5. And now we press graph, and we get a much clearer picture of what's happening. But remember, I want the custom values for our table here. If we look back at the table that we just made before, we need to know what's going on at 1, 5.25, 7, and 7.5. So to do this, I'm going to go back to second window. I'm going to change the independent variable from auto to ask, and I'm going to type in all those values. So I'm going to type in, we have x equals 1, we have x equals 5.25, we have x equals 7, and we have x equals 7.5. These are the values we need to analyze. So now we could see with this list that the absolute maximum value of g of x on this interval is occurring at x equals 5.25, and the absolute minimum is going to occur at x equals 7. Now, once again, one important thing to remember is that the critical points you look for, you have to remember the sneaky critical points. Notice here at x equals 7, we have a sharp turn. This is where the function g of x is not differentiable, but notice the absolute minimum occurred at this location. Question 4, we want to find the absolute extrema of w of x, and we're on the interval here from -3 to 3. So we want to use the extreme value theorem here, but in order to be able to use the extreme value theorem, we have to make sure that our function is continuous on this interval here. And the place that we could run into the most trouble would be at x equals 0. So first I would verify that w of x is continuous at x equals 0. And first we're going to have to find the limit as x approaches 0 of w of x. And this we could find by looking at the left side and right side limit at 0. And to find those, we could just plug in 0 to the top and bottom. And notice that on top, we get 2 squared plus 1 is 5. And on bottom, -1/3 times 0 plus 5 is also 5. So this tells us that the limit as x approaches 0 of w of x exists, and it's equal to 5. But notice that w of 0 is also equal to 5. So we could just say that the limit as x approaches 0 of w of x is equal to w of 0, which is equal to 5, which tells us that w of x is continuous at x equals 0. So now let's think about what does this function even look like. So we'll sketch w of x. So over here, I'm going to sketch w of x, and I notice that to the left of 0, the piecewise function is a quadratic shape, and it's in vertex form here in this top row. So the vertex of this quadratic is going to be at -2, 1. So I could go to the left 2 units like this, up 1 unit, and this is going to be the vertex of the quadratic piece. But notice that the quadratic piece stops at 0, and we graph the quadratic piece for all x values less than 0. So it's going to go like this. It's going to go up, and it's going to reach a height of 5. And then this way, if I go to the left, it's going to go all the way up forever, because we could just keep going all the way to the left here as x goes to -infinity. But once again, we found the limit as x approaches 0 was equal to 5. and we showed that w of x is continuous at 0. So I'm just going to put a solid point here and say that this is at a height of 5. And then after 0, to the right of 0, we have the equation here, or the expression negative 1/3 x plus 5. So then the function goes from quadratic to linear, and it's all connected. So this would be what the rest of the function looks like. So now we're on this interval here from -3 to 3. So if we look here, we just look at this picture from -3 to 3, we just have to find what is the absolute maximum and the absolute minimum. And just looking at this sketch here, it's looking like our absolute minimum is occurring at -2, and our absolute maximum is occurring at x equals 0. And remember, we're on this closed interval here from -3 to 3, but that's just by sketching. But now to be 100% sure, let's go ahead and find the absolute extrema using calculus. So we're going to find the derivative w prime of x. And for this, we're just going to take the derivative of the top and bottom piece. So the derivative of the top, we're going to have 2 times x plus 2. And technically, I would have to use the chain rule here, but the derivative of the inside is 1, so I don't have to write times 1 after. And then the derivative of plus 1 is just 0, so I could just stop here and say this is true for x less than 0. And now the derivative of the bottom, we're going to have negative 1/3 like this. But now I have to be very careful here. I can't say x is greater than or equal to 0. Okay, this would be a very, very dangerous argument. We're just going to say x is greater than 0 here, because if you notice on the graph, we have a sharp turn. And the sharp turn on the graph tells us that our function w of x is not differentiable at x equals 0. And this tells us that w prime is undefined at x equals 0. So that's why we can't put the equal to here with the 0, because we can't include this in the domain of w prime. But if we want to write a formal argument as to why w is not differentiable at x equals 0, we would have to analyze this limit over here. We would have to look at what is the limit as x approaches 0 of w of x minus w of 0 over x minus 0. So this is the limit definition of differentiable. So to find this limit here, we would have to analyze the left and right side limit. So we're going to take the limit as x approaches 0 from the left side, and w of x, if we look at the original w of x up here, if we're on the left side of 0, we're going to use this top piece here. And I'm just going to expand the top. So that's going to become x squared. And then if I expand this, I'm going to have plus 4x. And then I'm going to have plus 4. And then 4 plus 1 is going to give us plus 5. And then we have minus w of 0 is equal to 5. So I have 5 minus 5 on top. And that's going to cancel out. And then we're dividing by x minus 0, which is just x. So if we look at this limit over here, this limit's going to simplify to, we're going to have the limit as x approaches 0 from the left side, and on top I could factor out x, and we have x plus 4 like this, and we're dividing by x, and notice that x over x cancels. So now I'll just make a little bit of space for us, and now to simplify this limit, we're just going to plug in 0, and we get 0 plus 4 is equal to 4. Now the fast way to do this, if we don't have to write a formal argument, we could just plug in 0 to the top piece here and see that 2 times 0 plus 2 is 2 times 2, which is 4. But this is just, once again, a more formal way of arguing why that w of x is not differentiable at 0. We're going to show that this limit doesn't exist. So now to complete this, we're going to find the limit as x approaches 0 on the right side, but we look back to our original piecewise function here. On the right side, we're going to use this piece of the function, the negative 1/3 x plus 5. So we're going to replace w of x with negative 1/3 x and then plus 5, and then we write minus w of 0 was equal to 5 over, we have x minus 0 is x. And now 5 minus 5 cancels, and we're left with negative 1/3 x over x. The x over x's will cancel, and this limit simplifies to negative 1/3. So notice that our left side limit is equal to 4, and our right side limit is equal to negative 1/3. So since the left and right limits don't match, that tells us the limit as x approaches 0 of this expression here does not exist. And then what this tells us, it tells us that w of x is not differentiable at x equals 0, which means that x equals 0 is a critical point of w of x. So now the other type of critical point that we have to find is, where is w prime equal to 0? Now notice the bottom piece here will never equal 0 because it's just a constant. It's equal to negative 1/3. But the top piece here, we could say w prime of x is equal to 0 when, and we set the top piece equal to 0. We could set 2 times x plus 2 equal to 0. And this is going to give us here x is equal to negative 2. So this is one critical point over here, and x equals 0 is our other critical point. So now to close this question out, we're just going to plug in the critical points and the endpoints to w of x. So we'll make a table over here. So we have x and we have w of x, and we're going from -3 to 3. Those are the endpoints. And the critical points here occurred at x equals -2 and at x equals 0. So if we plug in -3 here, we could plug it into the top piece because -3 is less than 0. And we're going to get -3 plus 2 is -1, and -1 squared is 1, and then 1 plus 1 is equal to 2. So this is the y value here at x equals -3. And if we plug in -2 here, we could see -2 plus 2 is 0, and 0 squared plus 1 is just going to give us 1. So this is going to give us our y value here at x equals -2. And then for the rest, we're going to plug in, we have x equals 0. And if we plug in 0, remember, we did this in the beginning here. W of 0 is equal to 5. So this we could just write out here is equal to 5. And then we plug in x equals 3. We would plug that into the bottom piece here. If we do -1/3 times 3, that's going to give us -1. And -1 plus 5 is going to give us +4. So now we just have to identify what's our absolute minimum and our absolute maximum. And the absolute minimum occurs at x equals -2. And the absolute maximum occurs at x equals 0. Question 5, our last question. We want to find the absolute extrema of q of x on the interval from -4 to 4. And for this question, we'll use technology. So we could switch over to the y equals here, and we're going to type in the function. So we're going to press math, go to the right to ABS for absolute value, and we have x minus 2 on the inside. And then we get out of this by hitting the right arrow, we write plus, and we pull up another absolute value. And this time around, we're going to write x plus 3 on the inside. So when we press graph here, and I'll graph it in standard here from -10 to 10 in the x and y direction, I'm going to adjust the window to -4 to 4. So we're going to go here to the x minimum and switch it out to -4, and then we'll switch the x maximum to +4. And this will give us a better idea of what our function looks like. So looking at a graph of q of x from -4 to 4, we could see that this function has an absolute minimum of 5 on this interval, and the absolute maximum is going to be 9. That's the highest point on the graph. So how would we do this without a calculator? So to do this without a calculator, we have to look at absolute value x minus 2 and absolute value x plus 3 independently of each other first. So if we look at this function here, this is going to be the function x minus 2 when x is greater than or equal to 2, and it's going to be negative x minus 2 when x is less than 2. And the way I know this is I'm just thinking about what does this graph look like if I were to graph absolute value x minus 2. Absolute value x reaches the origin, that's the turning point of absolute value x. So if I replace x with x minus 2, that sends the absolute value graph to the right 2 units. So the vertex would be over here at 2 like this. That's the turning point. And then if we do this for absolute value x plus 3, we could see the piecewise function for absolute value x plus 3 is equal to, and on top here we'll have x plus 3 when x is greater than or equal to -3, and we'll have minus in parentheses x plus 3 when x is less than -3. And if I were to sketch this graph here, we would have the absolute value function shifted to the left 3 units. So we would have the vertex over here at -3, 0. So this is what the other part of the graph here would look like if we were to graph them both independently. But now to combine these two together, we're going to look here at this transition point of -3 and +2. So I'm just going to put -3 on the graph here of absolute value x minus 2, and I'll put +2 on the graph of absolute value x plus 3. Because now when we look at q of x here as one big piecewise function, we're going to account for these transition points, and we look at the intervals that are created. First we could look at x is less than -3. That's the first interval we could look at when we look at these two transition points. And then we have the interval between -3 and 2. So I'd have -3 is less than or equal to x is less than or equal to 2. And then the last interval would be when x is greater than 2. And I'm going to combine these now, but we have to be very careful. For that first interval, when x is less than -3, if we look over here, we could see when x is less than -3, we're on this part of the absolute value function for absolute value x minus 2. And when we're less than -3 for this part here, we could see that we're on the downward sloping part. So now we have to think about which piece would be involved here if we're less than -3. That's going to be the bottom piece here, the minus. We would have x minus 2 like this. And then we're going to add for the second piece here plus absolute value x plus 3. When we are less than -3, that's going to correspond to the minus, and we have x plus 3 like this. So that's going to be this first row. And now between -3 and 2, notice for the first graph here, we're still on this downward sloping part of the graph between -3 and 2. But then between -3 and 2 for the other part here, now we're on the upward sloping part here. So now when we combine these, for the first part here in purple, we're going to take the less than 2 piece, the minus x minus 2 is still going to be there. But then when we switch over to the red, notice now when we are between -3 and 2, we are greater than -3. So we're on this positive sloping line here, the x plus 3 line. So this is going to be our middle row. And then for the last row here, we're looking at that last interval when x is greater than 2. And for the first graph here that we drew, now we're finally on that upward sloping part. And for x greater than 2 in the red, we're still on that upward sloping part. So we would combine here the x minus 2 and then plus the positive slope here. This part of the piecewise function is x plus 3. So now we could just combine all this stuff and simplify. So q of x here we could simplify, and this is going to work out to, this part will be negative x plus 2 when we distribute the negative, and then this part here would be minus x minus 3 like this. So we have minus x is minus 2x, and then we have 2 minus 3 is minus 1. And then for the middle row here, notice what we're going to have is we're going to have minus x plus 2, and then we're going to have plus x plus 3. And notice that minus x plus x is going to cancel, and we'll just be left with 2 plus 3 is 5. And then for the last row here, we have x plus x is 2x, and we have negative 2 plus 3 is plus 1. And now we just have to transfer the intervals over. So we have x is less than negative 3, and then we have negative 3 is less than or equal to x, which is less than or equal to 2, and then we have x is greater than 2. So now let's compare our piecewise function to the graph. So if we look at this first downward sloping part here, this represents the line y equals negative 2x minus 1 when x is less than negative 3. And then for this line here, this is the line y equals 5. And then finally, if we look at this last piece over here, this is the line y equals 2x plus 1. So all the pieces we found are matching up. So now let's find q prime of x, and we're just going to find the derivative of each piece of this piecewise function. So the derivative of negative 2x minus 1 is just negative 2. The derivative of 5 is 0, and the derivative of 2x plus 1 is 2. But when we write down the intervals over here, we just have to be careful. We're going to write x is less than negative 3. And for this part, though, we're going to write negative 3 is less than x is less than 2. And then we're going to write x is greater than 2. The reason why we're leaving out these equal to pieces is because if we look over here at negative 3, we have a sharp turn in the graph, and at x equals positive 2, we have another sharp turn in the graph. So q of x is not differentiable at negative 3 and 2. And the reason is that the slope of this line goes from negative 2 to 0 immediately, and then it goes from 0 to 2 immediately, the slope. So since we don't have a smooth transition from the slope here from negative 2 to 0, that means that our function is not differentiable at negative 3 and 2. So now that we've identified the critical points here, now all we have to do is plug them back into the original function q of x, and we could also plug in the endpoints here, negative 4 and 4. So we have negative 4, negative 3, 2, and 4. These are going to go into q of x. So if we plug in negative 4, notice we could plug it into this piece right here. We're going to have negative 2 times negative 4, and then minus 1, and that gives us 8 minus 1, which is equal to 7. And then we could see when we plug in negative 3, that's in this middle piece here. When x is negative 3, the y value is 5. So we have y equals 5, and then at x equals 2, we still have y is equal to 5 here. And then if we look, we could see that when x is equal to 4, we would plug into this bottom piece here, and we'd have 2 times 4 plus 1 is equal to 9. So now we could just summarize everything. On the interval from negative 4 to 4, we could see q of x reaches its absolute maximum at x equals 4, and the y value there is equal to 9. And then the absolute minimum is going to occur between negative 3 and 2. All of these y values here of 5 count as the absolute minimum value. So we'll just mention the y value here. The absolute minimum y value is 5.